Okay, so we have these three polynomials, and I want to know if they are Li or Ld. Really quickly, if I only give you two vectors, do we have an easy way of deciding if they are Li or Ld? If I only give you two vectors? Correct. If it's only two vectors, it's easy because the two vectors have to be multiples of each other if they are LD. And by multiples, I mean scalar multiples. I can take one of them, multiply it by a scalar, and get the other one. That's with two vectors. But be very careful. As soon as I have three vectors or more vectors, like this has three vectors, I cannot use that check. I cannot say whether these are Li or Ld. So, for example, the first one is definitely not a multiple of the second one. It's definitely not a multiple of the third one. And the second one is not a multiple of the third one. There's no common multiples there, but that doesn't mean that they are Li automatically. As soon as there are three or more vectors, we're going to have to work a little bit harder to get the answer. Okay? So how do we do this? Okay, we put these vectors into the columns of a matrix, and it is very important that you put them into the columns, not the rows. Okay, so, and then when we're putting them into a matrix, you have to be a little bit careful. You're not going to put the x's into the matrix. The thing that you are doing with these polynomials is you're putting the coefficients into the matrix. So for example, the first polynomial, I'm going to put it in there as 2 for the constant term. There is no x term, and then there's a -1 on the x squared term. Now, by the way, somebody else might have said, you know what, I'm going to put the x squared term first, then the x term, and then the constant term. Both of these ways of putting that vector into that first column are okay, as long as you do the same thing consistently with all of the vectors. So just be careful that you do it the same way. I guess I'll just do it this way since I already started with this. Okay, so constant term first, then the x term, then the x squared term. So what's my next column of my matrix going to be? 1, 1, 1. Good. Okay, and what's the third column of my matrix going to be? Good. So yeah, there's sometimes going to be some zeros here like that. And then do I need to augment this, or what do I do? Augment with? What are we checking? Li, Ld. What do you put in the last column? All zeros, yes. If you're checking if these vectors span P2 of R.
There's another question, does this span?
Well, we'll get to that next, right? But for right now, is it Li or Ld? For the Li, Ld question, you put 0 there. If I wanted to know whether these vectors span P2 of R, I would have put like A, B, C there. Right. Okay. So this is for the Li question. So really you just need to row reduce this, but honestly what actually matters, because this is a square matrix, what you can simply do is find the determinant, as long as it's a square matrix. One thing that will be like a fatal flaw that I don't want anybody to do is to try to take a determinant of a matrix if it's not square. You can't do it, right? It has to be a square matrix, and by square I mean to the left of this bar. So let's just do this determinant real quick by the arrow method. Okay. I should have mentioned earlier that I'm not going to be focusing on questions from chapters 1, 2, and 3, but of course I expect you to know that material for this exam as well. So the determinant of this matrix, let's see, the first diagonal is 0, the next diagonal is going to be 1, and the next diagonal is going to be 0, and then I go minus -3, and then minus -2, and then minus 0. I'm just doing it quickly to save time, but you guys can check that later on. Do I get 0 or non-zero here? Non-zero. It's not 0. If it's not 0, then guys, what it means is that your matrix is invertible. It means when you do EROs, you are going to get pivots that go like that. Right? So, but we don't need to actually do those EROs, you see, because it's a square matrix. We can just take the determinant and go with it from there. Now, if this had not been a square matrix, If it was not a square matrix, then of course you cannot take the determinant of it. And you need to think a little bit about what would happen. Okay, let me come back to the non-square matrix thing in a second. Let's finish this problem first. So, based on getting a non-zero determinant, what would you conclude is the answer here? Li, right? Remember, guys, non-zero determinant is like a good thing. So all good things come together, right? If it's a non-zero determinant, it means the matrix is invertible. It means that the columns of the matrix are Li. They are a good set of vectors. Li is like a good thing. Okay. Is everybody okay with that? Now, if there had been a fourth column, what that would have meant was that we had 4 vectors. That would be k equals 4. In what vector space are we working here, by the way? What is my P2? Exactly. What's the dimension of P2 of R?
3.
Exactly. So, of course, you guys need to know your dimensions of your standard vector spaces. This is a 3-dimensional vector space. If I had given you 4 vectors, which would mean you have 4 columns there, then you would know that that's too many vectors, and that the vectors must be LD. And I would expect you to just write that down in about 10 seconds and go on to the next problem, right? You can spend your time if you want, if there's a 4th column here, you can spend your time and do, now you can't do a determinant because it's not a square matrix. You can spend your time doing all the EROs and finding out that there is a free variable, but you don't need to spend so much time, right? I suppose the exception to that would be if I asked you for a linear dependency. Remember when we had some problems about that? So I might not only, I could ask you, are the vectors Li or LD? And if they are LD, give me a dependency among those vectors. Well, then you really do have to go through the hard work. You can't just say, oh, 4 vectors in a 3-dimensional space must be LD, we're done. Because I'm asking you for more, right? So make sure that you know how to find and write down a linear dependency in cases where there is one. Not true here, but it could be. Yeah. Brandon?
For that answer, could we just put whatever the, I guess, like the multiple is times v1 plus like
to find the linear dependency. Okay, so maybe we need to review how to find linear dependency.
Well, no, just the way we present the answer. I'm not asking about how to do it. Just if we
what's the question?
Like if you want us to write out like half times v1 plus 2/3 plus v2, like can we just do that, or do you want us to write out?
Yeah, you can just do that, but
okay.
But you have to know how to come up with those, with the 1/2 and the 2/3 and all that, right?
Right.
Yeah. So maybe I'll. Maybe I have it on a review sheet somewhere. I probably should.
It's on the
Let me come back to that. That's something you definitely need to be able to do. Okay. So again, if I give you 4 vectors, this won't be a square matrix now, but you'll also know immediately that the vectors are LD without doing any work at all. What if I had only given you 2 vectors? Well, if I only gave you 2 vectors, then you only have 2 columns in this matrix. So again, it's not square. You cannot use a determinant. But now you have, you really do have to do the hard work of like figuring out where the pivots go when you row reduce the matrix. So if it's not a square matrix, you have to row reduce it. Okay, that's a common thing that comes up. Here we got away without that because it was a square matrix. We just took the determinant and we got our answer. Okay, everybody good with that? So it's Li in this case. And then the question, the second part of the question is, does the set span? So does S span P2 of R? So what would your answer be?
Yes.
Yes. Yes, and it's just that fast, isn't it? Why is it so fast?
Can you give us right or not effect?
You can just say, well, the determinant is not 0, so that also means that if I change this to ABC, it's okay. You don't get a pivot over in this last column. Another way to say it is K equals N, right? I have 3 vectors in a 3-dimensional space, and it was a thumbs up on the Li question. We already figured that part out. And if Li is thumbs up, then span is also thumbs up. Because remember, it's both or neither. If k equals n, it's both or neither. That's really, really important. Okay? Everybody good on that? So this is a quick one. It's definitely yes. All right. Okay. We're good on that. Okay, let's go on. Any questions so far? Part of what, the review is, I'm throwing questions at you, but it's also to sort of get your minds going a little bit. Think about, well, what are the questions you guys have? So be sure to interrupt me. Okay, let's go on to number 3. So here's what it says. Let's see. So show S is a subspace of V, or explain why S is not. Okay? So show that S is a subspace of V, or explain why it's not. So here's the first one, part A. V is going to be M23 of R. We're back to matrices again. These are the 2x3 matrices. And I'm going to let S be the set of capital A, element of M23 of R, such that the rows of A sum to 1. Okay. So these are all 2x3 matrices where the rows add up to 1. And the question is that a subspace of V? And if so, prove it. If not, explain why not. What do you guys think?
No.
Is there anybody who doesn't agree that it would be no? That's what we were going to say. Does everybody agree that it is no? Yeah, okay. So, you have to explain it. Convince me.
Zero vectors.
Your very first thing you always want to think about is the zero vector, right? If these, now in this context, okay, there's a problem on the sample test where the zero vector looks very, very different. But in this problem, the zero vector is literally, here is your zero vector, right? It's a 2x3 matrix, that's the vector space you're working in, so that's what your zero vector looks like. You look at that, you say, do the rows of that matrix add up to 1? You can clearly see that they don't. That doesn't need to be justified, that's obvious, right? So this is not an element of S. You just have to write that down, that's all, okay? So, no zero vector in S, so S is not a subspace. Okay, so that's all you got to say. When I'm writing my test and I'm thinking about how long it needs to be or should be so you have enough time to take it, I'm going to be writing a question like this thinking it's like 30 seconds or less. It's very, very fast. Don't spend a lot of time on that, right? Because you can give a real quick reason there. Okay, everybody good with that? Any questions? Any problems? Okay. Let's try part B. Let's take the same vector space again. So let's take V again to be M23 of R. And this time I'm going to take S to be the set of A, element of M23 of R, such that, and this time, the rows of A sum to 0. So when I add up the rows of the matrix, they add up to 0. Okay, so let me show you one idea. One idea would be, pardon? Oh, I was just going to say, if I take this same matrix again, I look at the 0 matrix and I say, oh, yep, the rows add up to 0. This is an element of S, right? Can I therefore say S is a subspace of V? No, it's not good enough. If you ever forget why that's true, just remember the parabola, right? 0, 0 is part of the parabola. It has the 0 vector in it, but that parabola is not closed under addition and scalar multiplication. So just because the 0 vector is there doesn't make it a subspace. It's still a good thing to check. Because like here, it was not in the set, and we quickly were able to just rule it out. In this case, the zero vector is in the set, and so I need to go on. I need to extend my analysis. So you really have to check whether S is closed under addition and scalar multiplication. Okay? Unless, okay, when could you avoid that? One time when you could avoid that would be if S was like a null space of a matrix. Right? So for example, if, okay, so this is, I'm taking a break from solving this problem to just make another point. Suppose that V was like R3, so this is just a side example. Suppose that V was equal to R3, and suppose that S was the set of X, Y, Z, so you had vectors in R3, such that, I don't know, negative 2x plus 6z was equal to 0, and x plus y minus z was equal to 0. Suppose you had that. Well, what you would hopefully realize here is that this set S is actually just equal to, it's not been presented this way, but it's really just the null space of that matrix. Anytime you have a null space of a matrix, it's a subspace of Rn. So you wouldn't need to show me closure under addition and scalar multiplication for this problem, because you could just cite that fact, that the null space of any matrix is always a subspace. Why? Because we proved it once. Actually, it was in the homework. So you guys actually showed it, that this is any, it doesn't matter what these specific numbers are. See, I can change these numbers all I want. It doesn't fundamentally change the concept that it's closed under addition and scalar multiplication. So instead of making us reprove it every single time we have a set that looks like this form, we just prove it once and for all that any time you have the null space of a matrix, it's a subspace. Done. No need to check any further. Now that's not what we have up here though. Notice that our set S is not even a subset of Rn. The vectors in this problem are actually the matrices. Whereas down here the vectors were these triples of numbers. They were in R3. So, so on the problem that we're looking at up here, and really for any example that involves, you know, polynomials or matrices, you have to do it the hard way. You have to check the closure under addition and scalar multiplication. Okay, so how am I going to do that? We should maybe write down what the vectors look like that are in S. That's exactly right, the general form, right? So a vector in S has the form. Who thinks they know what kind of form we're talking about?
A, B, C.
Okay, so capital A. I'm just going to give it a name here. So what would the first row look like?
A, B, minus A, B.
A, B, and
minus
of A plus B. Remember, it has to cancel out to 0 when I add up that row. Okay, and then on the second row, it's going to be what? C, D, and negative C plus D. So basically you have three choices in the first two columns, and then the last column is required to make the row add up to 0. So you have no more choices. So this is basically the form, right? Okay, so if we have that, then what we can do is take two matrices that are of that form and add them together and just see if it still has that form. So let's do that, okay? So if, so for closure under addition, and it's very helpful when you're writing these up if you break your two sections apart so I can see them clearly. Closure under addition, so I'm going to say, you know, let capital A be equal to, you know, little a, little b, negative A plus B, and then C, D, negative C plus D. And then I need a second matrix, I'm going to call it capital B, And now I need to use totally different letters, right? Please do not reuse the same letters. They need to be different letters. So let's say I'm going to use like x, y, and negative x plus y. And then on the bottom row, maybe z, w, and negative z plus w. And we're going to let those be in S. Guys, you have to be willing to put some words in there. Okay, if you don't write any words, it's very, very hard to read your mind as to what you were thinking. Right? This needs to be, I'm not expecting this to be, you know, sort of mathematics journal quality writing. Right? That's what professional mathematicians have to do. But I do expect it to be comprehensible. It means you have to put some words in there. Right? So you have to set it up for me, like that. Okay, so then A plus B. We just add these guys together and we do it slot by slot, right, in the usual way. So A plus X, then B plus Y, and then negative of A plus B plus X plus Y. I'm just going to algebraically add together everything. Okay, on the bottom row, I'll have C plus Z, and then D plus W, and then negative of C plus D plus Z plus W. So this is the sum of A plus B. And then we just simply have to look at that. And we have to say, do the rows add up to 0? Do both rows add up to 0? Absolutely. So if both rows add up to 0, and I think that's clear, like you don't need to stop and like prove it to me. I can see that they add up to 0. So then what else do I need to write here? Yes, you have to put element of S in there. Very important that you draw that conclusion, that it is an element of S. Very good. Okay, so the closure under addition works. Okay? All right, and then, of course, the next part is the closure under scalar multiplication. Closure under scalar multiplication. For that, how do we start off? Excellent. Let A be as above, and K is an element of the real numbers. It's like a constant, right? K is a real number constant. Okay? So then we just have to take K times A. K times A. All right, that's easy enough. We're just going to take the matrix A and multiply it through by K everywhere. So we will get KA, KB, negative K times the quantity A plus B. And then on the bottom line, KC, KD, and negative K times the quantity C plus D. And again, we just have to look at that result and say, do the rows add up to 0? If you can mentally convince yourself of that, then you would just say element of S. You have to say that and put a check mark there. Please try and format it consistent with the way I'm doing it here. I don't want people just doing their own thing because I can't read your mind what you're trying to say. Or at the very least, you should write out the words. So you could say, therefore, since S has closure under addition and closure under scalar multiplication, S is a subspace of V. V is M2, 3 of R. Right. Okay? Everybody good with that? I have a question for you. Does anybody know a different way to show that S is a subspace, in this example, that S is a subspace of M2, 3 of R? Or like a fancy way to do it? If not, that's okay.
So like row space or column space?
No, it's not that. Row space and column space, you'd have to have a, remember row space and column space had to do with Rn and Rm, right, which is not the space we have here. Okay, I'm going to come back to that question in a second. There is another way to do this problem. I like this way. You guys need to know how to do this approach, but there is another cool way to do it. And I'm going to show you in a second. You can be thinking about that. What I want to do in the meantime is ask a part C. Okay, part C says find a spanning set. Find a spanning set for S in part B. How do I find a spanning set? Bust out from what?
The
A matrix.
This one right here. So maybe in your notes you could put like an asterisk in your notes to refer back to that. And then I'm just going to say, so go back to where you wrote that down, and then I'm just going to say, using star, we bust out the variables. Maybe we can go straight to the answer. Are you guys good at busting things out and sort of going straight to it? Let's look at it. I claim that, okay, well, let's just try it. If I bust out the A, which is my first variable. By the way, how many variables are there to bust out?
4.
4, right? So I would be expecting 4 vectors here. What would be the first one?
1, 0,
1, 0,
negative
-1, all zeros, 0, 0.
Right? You just look at where the A's are and put the coefficients in there. Okay, what about when I bust out the B?
0,
0,
1,
1,
negative
negative 1, 0, 0.
Okay, like that. And then I need a little bit more room. Okay, so the third one would be
all zeros on the top.
all zeros on the top and
1, 0, negative
1, 0, negative 1 on the bottom. Good. And then the very last one?
1. All zeros on the top.
All zeros on the top.
0, 1, negative 1.
0, 1, negative 1. There you go. That's a spanning set. Make sense? By the way, in this case, we don't really know the dimension of S ahead of time. This is not like a standard vector space that we're looking at. V is a standard vector space. I think everybody would know the dimension of V. What is the dimension of V? 6, right? 6 entries. But S is not like one of these standard vector spaces we work with all the time. So I wouldn't expect people off the top of their head to know the dimension of S. But of course, once I have this spanning set, then I know that, okay, these 4 vectors are already halfway to a basis for S, right? And it would just simply be a matter of checking if they are Li or not. See remember that table where you have K is less than N, greater than N, or equal to N? That table is wonderful if you know what N is. But if you don't know what N is, you can't use it. So K is 4. I have 4 vectors here. But the question is, what is N? We don't actually know what N is because we're not working with a vector space that we've ever worked with before. So in that case, if you don't know what N is, then you have to question, are these a basis or not? They're definitely a spanning set, but they're not necessarily a basis. So I would have to check for linear independence. Maybe I should do like a part D as a follow-up here. Okay, let me just do a quick. Maybe you can tell, but there's 4 of them, right? So it's not totally obvious. So just as a quick follow-up. Okay. Let me label this set of 4 with like a double star. So then I could say, is double star a basis for S? They're already a spanning set, but that's only half of what it takes for something to be a basis. They also would need to be Li. So what we would do to check for Li is we would put these vectors into the columns of a matrix. And I'm just going to go across the top row, left, middle, right, and then bottom row, left, middle, right. So the first column would be 1, 0, negative 1, 0, 0, 0. So a single matrix gets put into that column. The second matrix would be 0, 1, negative 1, 0, 0, 0. The third one would be 0, 0, 0, 1, 0, negative 1. The fourth one would be 0, 0, 0, 0, 1, negative 1, and then I would augment that with all zeros. This would be your matrix that you have to row reduce. Okay? Everybody following that? Everybody see how I did that? Slow me down if I'm going too fast. There's no hurry here. You can already see you're going to get pivots there and there, first 2. And then by taking multiple